Welcome back, everyone. If you've been working in AI or natural language processing lately, it honestly can feel like transformers and attention mechanisms have just always been here, right? Like they're completely running the show. But that is definitely not the case. Okay, let's dive into this explainer and look at how sequence modeling actually evolved before attention took over the world. We are going back to the foundational era of deep learning for text, a period that literally set the stage for everything we do today.
Here's a quick look at our roadmap for today. First, we'll hit the word order problem. Second, TextCNNs. Third, RNNs, LSTMs, and GRUs. Fourth, the limits of recurrence. And fifth, when you should actually still use these legacy models today. So we're going to unpack the core problem, the legacy architectures that tried to solve it, the mathematical pitfalls they ran into, and then give you a practical checklist for modern use.
All right, Section 1, the word order problem.
So to really understand why we needed advanced text architectures, we have to look at what came before them. Early embedding methods, think TF-ID or Word2Vec, they basically just threw words into a mathematical bag. To a flat vector model, dog bites man and man bites dog look exactly the same. I mean, they contain the exact same tokens. But obviously, word order carries the true signal here. One of those is just a normal Tuesday, and the other, that is front page news. If your architecture can't see the order, it absolutely cannot capture the meaning.
Moving on to Section 2, TextCNN, fast and parallel. So between 2014 and 2017, two heavyweight architectures emerged to fill this sequence gap. The first was introduced by Yoon Kim in 2014, the TextCNN. It applies 1D convolutions over sequences of word embeddings. Just imagine a sliding filter, let's say with a width of 3, moving across your text. That filter is essentially acting as a learnable trigram detector. It spans 3 consecutive words and outputs a score. And you can stack different widths together, like 2, 3, 4, and 5, to detect patterns at multiple scales. Then you use global max pooling to pick the strongest activation. And because of this max pooling, it literally doesn't matter if the phrase "not good" appears at the very beginning or the very end of a movie review. The detector still fires. The best part? This architecture is completely flat and parallel, meaning it trains incredibly fast because there are 0 sequential dependencies.
Which brings us to Section 3, RNNs, LSTMs, and GRUs.
While TextCNNs are parallel and flat, the other major approach from this era went in the complete opposite direction. Think of a recurrent neural network, or RNN, as a model that reads a sentence exactly like you do, one word at a time, moving from left to right. At each time step, it updates what's called a hidden state. And this brilliantly illustrates the core power of recurrence. That hidden state at the final time step acts as a mathematical summary of the entire prefix that came before it. Because it processes step by step, it can handle highly flexible input lengths. For classification, you just pool across those hidden states to make your prediction. Simple, right?
Well, here is where the story gets a little tense. Imagine feeding an RNN a sequence that's 100 tokens long. What happens to the information from token number 1 by the time the model reaches step 100? Let's say we're trying to predict if a specific word appeared anywhere in that sequence, and the model has to pass that gradient signal all the way back from the end to the very beginning.
We hit a massive mathematical brick wall. It's called the vanishing gradient problem. It's essentially a terrible game of telephone. The gradient from your loss function has to flow backwards through 99 sequential multiplications of the recurrent weight. If that weight is even slightly less than 1, well, multiplying a fraction by a fraction 99 times means the signal effectively vanishes to 0. The model completely forgets those early tokens. Conversely, if the weight is more than 1, the gradient explodes to infinity. So a plain RNN simply cannot learn long-range dependencies.
To fix this giant gradient cliff, researchers introduced 2 brilliant upgrades. The LSTM, or Long Short-Term Memory Network, solved the problem by adding a cell state. Think of this as a highway running straight through the network with only additive interactions. It uses 3 gates, an input, a forget, and an output gate, to carefully control what information gets added or removed from this highway. This stabilizes gradients through those long sequences. Then we have the GRU, which achieves similar stability but simplifies the whole architecture down to just 2 gates, meaning fewer parameters for you to train. Both of these gave us stable training through sequences of 100 steps or more. A total game changer.
All right, Section 4, the limits of recurrence. So LSTMs and GRUs were a heroic fix, but despite their brilliance, they had 3 fatal flaws. First, the sequential bottleneck.
If you have a sequence of length 1000, you have to do 1000 serial forward and backward steps. You simply cannot parallelize this across time, which is painfully slow on modern GPUs. Second, the fixed size context vector. In encoder-decoder setups, the model tries to compress the entire input into one final hidden state. Long inputs just get blurred and critical detail is completely lost. And third, the distant dependency ceiling. Even with that clever cell-state highway, LSTMs still struggle to propagate specific information across 200 or more steps. The accuracy just drops off a cliff. To overcome these limits, a massive pivot was absolutely necessary. And that is exactly why transformers completely dropped recurrence in favor of attention.
Let's head into Section 5, when to use them today.
Now, before you go deleting all your LSTM code, let's put our engineer hats on and be a bit pragmatic here. We absolutely shouldn't throw these legacy models away just yet. While transformers are incredibly powerful, they are wildly GPU-heavy, and they require the full sequence up front just to calculate attention. Contrast that with TextCNNs and RNNs. These are CPU-friendly, they're incredibly lightweight, and in the case of RNNs, they're capable of streaming single tokens one at a time. It's a classic trade-off, really, between heavy resource demands and lean, constrained hardware benefits.
So the crucial point is this actionable checklist. When do these legacy models still easily beat transformers? Number 1, edge or on-device inference. A TextCNN with glove embeddings is 10 to 100 times smaller than a transformer. If you're deploying to a mobile phone, this is your stack, period. Number 2, streaming classification. Because RNNs process token by token, they went hands down for real-time incoming text. Number 3, tiny baselines. You can train a TextCNN in literally 5 minutes on a basic CPU just to validate a dataset. Try doing that with a transformer. And finally, sequence labeling with limited data. If you only have, say, 1,000 to 10,000 labeled sentences, a LSTM CRF is still a highly reliable, production-grade architecture that won't overfit like a massive model would.
Which brings us to our final thought for this explainer. Look at the modern AI landscape for a second. We reach for transformers by default for almost everything. But considering that constrained hardware demands leaner architectures and considering the incredible efficiency of models like TextCNNs and LSTMs, are transformers always the right tool for the job? Sometimes the smartest engineering decision is actually knowing when to use the legacy tools that still pack a serious punch. Keep that in mind for your next project, and I'll see you in the next explainer.